Okay, hello everybody. This is going to be part two of a three-part series in which I look at a couple of old recovered TI 994A basic programs. What happened was that when I was a kid, I had this system, rather my dad had it, and he wrote a bunch of programs and I wrote some programs and we saved them all on cassette tapes. And a few years ago, I found these cassette tapes and digitized the audio from them, posted that audio to YouTube, and some very nice people were able to recover some programs from these audio files that I had posted to YouTube. Specifically, this person by the name, who I know only by their, I don't know if it's their name or their initials, CAS, could be CAS, could be initials CAS, recovered this program called Formulas, which I'm going to copy right now and paste into an emulator. So pardon me while I do that. Just want to make sure the whole thing's highlighted here. I asked my dad about this program, and he said back when I was a kid, he was an electrical technician at Ball Metal, Ball Corporation. They have Ball Aerospace and Ball Can Division. My dad worked for the Can Division as an electrical technician, and he said he created a program to help train new electrical technicians on the use of formulas. So this is a program that I believe my dad wrote called Formulas. I'm going to paste it into the emulator here. I'm a little worried that maybe part of the program is being cut off. You can hear those beeps that are happening occasionally, so I worry that maybe it's truncating a last part of one of these lines. I checked the code, and the lines that are the longest lines probably don't affect the program very much. So if that's the problem, I think we should still be okay. So apparently this is a program my dad wrote to solve electrical formulas. There's also, I think, the Pythagorean Theorem in there. So let's start it up. And we might begin and end the program a few times so we can see some of the boundary conditions. There are these cute little messages that pop up when you end the program depending on which formula you're on. So let's run the program. It'll take a second for it to process, and then it will get started. Any second now. There we go. Okay, please enter your name. So I am Zachary, the son of George Fruhling, who wrote this program as far as I know. Which of the following formulae do you request? Ohm's law, power, power factor, three-phase power, the Pythagorean theorem. I noticed the misspellings here. It's usually the Pythagorean theorem, but this is misspelled Pythagorean's theorem, U-M. It should be T-H-E-O-R-E-M. And I don't know what dB, decibels in milliwatts, decibels in millivolts, maybe, perhaps. I'm not sure what 6 and 7 referred to. I do know Ohm's law. I'm a ham radio operator, and I haven't thought about this in a long time. I do know the power formula. I can't recall power factor. I know almost nothing about three-phase power. I definitely remember the Pythagorean theorem, and we'll see what 6 and 7 refer to. So let's start with Ohm's law. For which unknown are you trying to solve in this equation? E equals I times R. Now, in Ohm's law, E equals voltage. E stands for electromotive force. I stands for current in amps. And R stands for resistance in ohms. So let's say we're trying to solve for the voltage. That means we know the current and we know the resistance. So let's say we've got a current of 2 amps. And I tested this beforehand. You have to use a comma to enter more than one value here. So let's say we have 2 amps and let's say we have 50 ohms of resistance. What should the voltage be? That should be 100 volts, right? 2 times 50. And sure enough, voltage equals 100. Do you wish to solve another equation? Yes, let's do that one again, just for completion's sake here. I'm not sure what the delay is there. Dramatic pause, I guess. I'll have to see what's causing that. Let's check out Ohm's law one more time. Let's say we're trying to solve for resistance this time. That means we know the voltage and we know the current. So let's say we have, 1,000 volts. And let's say we have a current of 3 amps this time. What should that give us? So it should be, resistance should be voltage divided by current. So it should be 1,000 divided by 3, or 333 and a third ohms. And that's what we get. Notice we get a nice repeating decimal here that's truncated. Do you wish to solve another equation? Now I'm going to end the program here just so we can see some of the cute messages. So no, let's say no, we don't want to solve another equation. Oh, Zachary, have a good day. Okay. That's not the cutest message. I've seen each formula generates a different cute message. There's a missing space there too. I'm not sure what happened there. Zachary, have a good day. Clearly, this program is mostly finished, but was never really polished. So Zachary, which of the following formula do you request? Okay, let's look at the power formula this time. Which version do you need? W is wattage, so power in watts equals voltage times current. And then there are a couple other versions of this. Wattage equals current squared divided by R, and wattage equals voltage squared divided by R. I'm sorry, the second one was wattage equals current squared times R, and number 3, wattage equals voltage squared divided by R. I think I messed up the way I said that originally. Let's just do the simple one up above. For which unknown are you solving in this equation? W equals E times I. So let's say we're solving for the wattage. We know the voltage. Let's say, I don't know, 120 volts. And let's say 2 amps of current are being used. And so we get a wattage of 240 watts. So let's do that again. Okay, we are going to do power formula again. Let's do the second version this time. Which unknown are you solving for in this equation? Let's say we're going to solve for resistance this time. What are the values of the wattage and the current? So let's say we're using 100 watts at 2 amps. That gives us 25 ohms of resistance. Pretty straightforward. Let's see what error message we get, or not error message, what goodbye message we get if we say no, we don't want any more. More power to you. Poof. This is my dad's sense of humor for sure. This is part of the reason I knew my dad wrote this one, because it has my dad's sense of humor built in. More power to you, because we're solving for the power formula. Poof. Like, too much power. You blew yourself up, I guess. Okay, let's see. Let's run the program again. And I'm going to have to punt on the explanation for some of the formula. I just don't know power factor, and I don't know three-phase power. I'm embarrassed to say that I don't know those things. If I knew them at one point, I've completely forgotten them. So let's see. Zachary, which of the following formula do you request? Let's say power factor. You know what? Before I move on, what I love about this program is these early programs are a window into how early personal computer users thought that the computer would be useful. So here's an example, not just of a game on the TI, because everyone had games on the TI. People bought games on cartridges, people wrote their own games, people typed in games from magazines. But here's an example of a TI 994A program actually being used in industry to solve a practical problem for training purposes in a real industry environment. My dad said he wrote this program for use at Ball Metal Corporation to train new electrical technicians. This is, think about that. Think about all the online training you do now to learn various things at your job or in school or in college, whatnot. And this is in the early 1980s. A computer was being used for training purposes in a practical industry like that. Really forward-looking. Okay, so power factor. Okay, let's see. Kilowatts equals actual power measurement with a kilowatt meter. kVA equals apparent power with measurement of voltmeter and ammeter. Okay. I guess this is because of the inefficiency of certain things like motors and whatnot. For which unknown are you trying to solve in this equation? Power factor equals kW, which is power measurement with a kilowatt meter, versus kVA, apparent power. Kilovolts apparent, I guess what kVA stands for. So let's say we want to solve for the power factor. I think what we're going to do, let's say we have 1,000, not 1,000, that's unrealistic, right? Let's say we have 1 kilowatt and we have 0.9 kilovolts. Let's see, kilovolts apparent. Okay, no, that's... What am I doing here? Power meter. Okay, that is the power measurement with a kilowatt meter. kVA, that's got to be kilovolts apparent. So we're going to redo this, actually. Let's say we have 1 kilowatt, and the kilovolts apparent, let's say we've got 240 kilovolts apparent. I'm not sure I've plugged in realistic values or not. If not, I apologize to anyone who does know how this works. The power factor equals 0.004166666666 and so on. Okay, let's try that again. Again, I'm not really sure what realistic values would be here in industry, so maybe put in the comments if you do know how power factor actually works. Okay, so kilowatts equals actual power measurement with a kilowatt meter. kVA, it's got to be kilovolts apparent. Yeah, voltmeter and ammeter. Actually, let's see here. Now that I think about it, kVA, that might be voltage times amps. How many thousands of volts times amps? Because voltage times current would be wattage. So, yeah, I think really what we're going to do is something like this. I think this is probably more realistic. Let's say we have 1 kilowatt, but we have 0.9 actual power. What would the power factor be? Oh, it didn't like that for some reason. Oh, here we go. I entered the wrong. I want to solve for the power factor. That's what I was entering. So we have 1 kilowatt and we have 0.9 kilowatts apparent. Power factor computed to be greater than 1.0. Please check your data and then re-enter. Okay, so maybe we have that backwards. Maybe we have, out of a kilowatt meter, we have 1 kilowatt, but we're actually using 1.1 kilowatt. Ah, that makes sense. The power factor would be 0.909090 repeating. Okay, interesting. Something to learn. I feel like I should go study that now. Do you wish to solve another equation? No, let's say we're done for now. What cute message do we get? If you need more assistance, just whistle. That sounds like my dad, too. My dad would always be willing to help anyone who needed help. So if you need more assistance, just whistle. Let's move on to the other formulas. Formulae. I think it's formulae. Although in Latin it would be formulae. Okay, enter your name, Zachary. So let's do 3-phase power. And again, I'm out of my element here. And part of the reason I know my dad wrote this is that they use 3-phase power in industry and anytime there's big machines because it's more efficient and efficient use of electricity. Okay, 3-phase power, number 4. Oh, it didn't like that. Bad line number in 3090. Let's list 3090 real quick and see if we can figure out what went wrong here. Go to 3010, list 3010. Okay, what's the bad line number there? Oh, there is no 3010. Aha, so we do have a little typo in this program. That's okay. I'm not going to try to fix it right now. I just want to document the state of this program when I encountered it. We could actually come over here and look at the code, though. So, let's see. I already forgot the line numbers. Oh, well, we'll try it another time. Zachary. Okay, so it looks like we can't do 3-phase power right now. Doesn't like the go-to line. So maybe my dad was in the process of working on this program, but I suspect that might have just been a typo. So let's say the Pythagorean Theorem. You know what I like about the Pythagorean Theorem here, look at how careful my dad was at creating a little triangle on the screen here visually. So he had to define character codes for this diagonal line. He had to define character codes for the endpoints of this diagonal line, and then of course the lines on side C and B here are just I guess you had to define characters for those as well. Those are just horizontal and vertical lines defined as characters. Okay, so for which unknown are you solving this equation? So a equals the square root of b squared plus c squared. And of course, if you don't know your square roots, taking a square root of something is the same thing as raising it to a power of 1/2. So that's what's going on here. Probably could have found a nicer, friendlier way to write that. So let's say we're solving for a. We want to find the hypotenuse. So let's say it's a 3, 4, 5 triangle. So let's say one side is 3, the other side is 4, and we should get a hypotenuse of 5, and we do. Yeah, let's do that again. That was fun. Okay, so Pythagorean Theorem. I really like the way that graphic was drawn. It's really hard to, this is just a perfect 45-degree angle, but it's really hard to come up with graphics for weird lines at weird angles in the TI-9948. There's no built-in function for doing that in the system. So let's say we want to solve for C this time. And we know, let's see here, A was the hypotenuse, right? Which is weird, because usually it's a squared plus b squared equals c squared, but a was the hypotenuse. So let's say we know the hypotenuse is, we're just going to pick some weird numbers here. Let's say it's 15, and one of the sides is 7. What will the other side be? 13.26666. So on and so forth. Do you wish to solve another equation? No. Let's see what happens when we say we're done with the Pythagorean theorem. Just keep on the side with the right angle for half a square deal. I think there's a joke in there somewhere. Just keep on the side with the right angle for half a square deal. Don't be a square, I guess. It's okay. You half a square. Well, that's too bad we couldn't get one of these to work. I could try to fix the program, but I might do that in another video. I'm not gonna do that in this recording. So please enter your name, Zachary. Okay, we're in unfamiliar territory here. So let's say, I think dB means decibels, and so decibels related to milliwatts. I'm not sure about that. Hello, Zachary. For which unknown are you trying to solve in this equation? dB milliwatts equals 10 times the log of P2 divided by P1. So yes, it must have to do with if you have two power levels, it looks like it's trying to calculate the decibel relation, because if memory serves, every 3 decibels is doubling the power. So we could test that. We could say, let's say we have, okay, we're going to solve for the decibel increase. Does it take dB? Yeah, it does. Okay. Wasn't sure what the expected response there is. So let's say we have a 2-to-1 relationship. So let's have 2,000 and, oh, actually, I got these backwards here. P1, let's call that 1,000. And P2, let's call that 2,000. I think this should be an increase of 3 decibels. I'm not 100% sure. Yeah, right about 3 decibels. So I'm not sure what's going on here. I think it works out exactly, but maybe there's some rounding stuff going on with how the TI calculates a logarithm. But, oh, we have another typo here. Do you wish to, Joe, solve another equation? Yes, I do. I want to do that one again. Well, at least I remembered how decibels work. I couldn't remember anything about 3-phase power or power factor, but I apparently remember how decibels work from my work in ham radio. Okay, so let's see if it works the other way around. So what happens if we have 2,000 and 1,000? I think that should be minus 3 decibels, a reduction of 3 decibels. Ooh, I didn't like that. Oh, for which unknown? I got to do dB again. I keep doing that. Okay, so 2,000, 1,000. I think this should be minus 3 decibels. And it is. Okay, so I apparently remember how decibels work. And what happens if we say no? What cube message do we get? Well, Zachary, I guess this logs up another one. That's funny because it uses logarithms. And of course, this is a ham radio joke because, when you make a contact, you put it in the log, your logbook. So we just logged something else here. Cute little play on words with log meaning logarithm and log meaning logbook and ham radio. So that was cute. Okay, run. Now, I think it's going to work the same way with decibels as it relates to voltage. But let's take a look. I guess what I don't know is how that's useful in an industry context where my dad worked at Ball Metal. So I don't know if he just tacked those in because he thought that would be fun or he put them in because they were genuinely useful at Ball Metal. Okay, again, I don't know what the weird delay is there. Maybe it's just a dramatic pause. Maybe there's something else going on behind the scenes. Well, Zachary, for which unknown are you trying to solve in this equation? Decibels, in terms of millivolts, equals 20 times the log. Okay, so I'm not exactly sure how this works. The formula is different, so maybe decibels mean something slightly different as it relates to voltage. So let's say we want to solve for dB, decibels again. What are the values of E1, E2, enter in volts? So let's say voltage 1 is 60 volts, and let's say voltage 2 is 120 volts. Now, when we were talking about wattage, we said that doubling the wattage was a decibel increase of 3. I'm not sure if this works the same way, and it doesn't apparently. Apparently, it is a decibel increase of 6, and I'll have to ask my dad about why that's the case. I can call him on the phone and go, explain this to me, please. Yeah, let's do that again. Why not? Yeah, it makes me want to fix the problems in the program so I can have a totally working version of this program. But, for archival purposes, I want to capture what the program was like in the state that I recovered it from the audio cassettes that it was stored on. Okay, let's say we want to solve for E2 this time. What are the values of the decibel increase and E1? So let's say the decibel increase is 12 decibels and voltage 1 was 120 volts. Okay? Can we figure out what this would be? If, I guess we can kind of figure out what E2 should be, right? Just from these values. I want to kind of check my own work here. So we said that doubling the power is a decibel increase of 6. So if you double it twice, that's what it would take to get to 12. So let's see, 120 times 2 is 240, times 2 is 480. So my guess is 480, and maybe I'm misunderstanding something, but let's see what happens here. About 480. All right. So again, there's some weird rounding error with the logs. I think this should come out exactly. So I'll have to see how the TI handles logarithms and see why we're getting this weird approximation of the answer instead of the actual answer. In any case, no, I don't want to solve another equation. Zachary, I'm finished if you are. And I say we should end the program on that note. I want to list the program one more time. So I may create a blog post about this, in which case I'll post the entire code. So it may not happen right away, but if you're coming back and checking out this video at some point in the future, look in the description. I'll try to post a link to the blog post if I write a blog post and post the entire source code for this program. Maybe the original version and the corrected version even. But I'm going to let this... in fact, maybe we can keep an eye out for what the cute little goodbye message is for the power factor. Three-phase power, three-phase power. Maybe it's just have a good day. No, that's the first one. Okay, here we are. We're on the power formula. Okay. Eventually, we're going to get, I think next was the power factor. More power to you. Poof. Think how challenging it would be to solve these equations on your own. You got to find a calculator or do some math on the paper. And, this is way more convenient. This is a really forward-looking use of what computers are useful for. going to keep an eye for the... Okay, that's the power factor, so it should be coming up before too long. Okay, if you need assistance, just whistle. We looked at that one. So what's the goodbye message for three-phase power? Okay, there's the equations. Okay. I hope I can be of assistance again sometime. Okay, that was pretty straightforward. We're almost done. Let's let this program continue. So for the meantime, if you want to, if you were inclined to recreate this program, you could type this in yourself, conceivably. But I don't think anyone's actually ever going to do that. But I thought I would list out the program for completion's sake. Quite a lengthy program. I mean, this is, for a simple program, this is the thing about TI Basic. You can't combine line numbers on the multiple statements on the same line numbers. So there's a lot of line numbers for a fairly simple program. But I like that it's easy to understand. Notice there are no subroutines. My dad uses goto a lot. I tend to favor subroutines. I think they're a little easier. But he used goto statements here. There's our logarithms. And there we go. That's the entire formulae program. Well, everyone, thank you for watching. I hope you appreciated this little trip down memory lane. It's not a terribly interesting program, especially if you're not interested in electronics or electrical equations in any way, shape, or form. But I want to emphasize that this is an example, an early example of how people anticipated personal computers could be useful in an industry environment when that wasn't common at the time. No one was doing that in the early 1980s. And so this is also a great example of a TI Basic program that is not a game but solves a practical problem in a real industry. And, I'm glad my dad put his own little sense of humor in there. I try to put my own sense of humor into every program I create as well. So clearly I inherited that from my dad. Anyways, thank you very much for watching. I hope you enjoyed this look at formulae for the TI 994A in TI Basic. Have a great day.